Hey guys, I'm Voilen and welcome to day 8. I'm a little bit later today, but let's see. So, day 8, resonant collinearity. Okay. Collinearity. Okay. So, you'll find yourself on the roof of a top secret Easter Bunny installation. While the historians do their thing, you take a look at the familiar huge antenna. Much to your surprise, it seems to have been reconfigured to emit a signal that makes people 0.1% more likely to buy Easter Bunny brand imitation mediocre chocolate as a Christmas gift. Unthinkable. Scanning across the city, you find that there are actually many such antennas. Each antenna is tuned to a specific frequency indicated by a single lowercase letter, uppercase letter or digits. You create a map, your puzzle input, of these antennas. For example, so I think this is test data. Let's quickly add that to the test data. Okay, so the signal only applies its nefarious effect at specific antinodes based on the resonant frequencies of the antennas. In particular, an antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This means that for any pair of antennas with the same frequency, there are two antinodes, one on either side of them. So for these two antennas with the frequency A, they created two antinodes marked with hashtag. Adding a third antenna with the same frequency creates several more antinodes. It would ideally add 4 antinodes, but 2 are of the right side of the map, so instead it only adds 2. Wait, adding a third antenna with the same frequency creates several more antinodes. It would ideally add 4 antinodes, but 2 are off the right side of the map. So instead that adds only 2. Okay, this is kind of confusing me right now. Antennas with different frequencies don't create antinodes. A and A count as different frequencies. However, antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinode but has a lowercase a frequency antinode at its location. Okay, this is getting very complicated. And the first example has antennas with 2 different frequencies, so the antinodes they create look like this. Plus an antinode overlapping the topmost A frequency antenna. Okay, so this is not the test data then. Because the topmost A frequency antenna overlaps with 0 frequency antinode, there are 14 total unique locations that contain an antinode within the bounds of the map. Calculate the impact of the signal. How many unique locations within the bounds of the map contain an antinode? This is probably the first time that I have this, but I have no idea what I have to do. What is the test data then? Because topmost frequency A, antenna overlaps with 0 frequency antinode. There are 14 total unique locations that contain an antinode within the bounds of the map. I have no idea how to do this. Okay, I think I understand what I need to do now. So for part 1, first of all, let's get the data. Okay, next up, I think we need to get all possible antennas. I'm not 100% certain if we have... yeah, so... var L antennas. Okay, so over here we just change this into a function. So a new L array data. So if you get all the names of the antennas, it will be easier to check the different locations of each one. I think we should make a dictionary and save the locations of where they occur. So let's create a dictionary in a data.size. I think the data is equal, so 1212, yeah. So we have that amount of log that it's still like an exact square. A data.size. If it's a dot, we just continue. Continue. And let's just append a vector to I with X and Y. And else this would be an array starting with this one. Okay, and with this we should normally get all the data, so we can quickly test them by printing the L antennas. Okay, let's see what we get. An error. Okay, let's see if this works. Okay, so we get some amount of data, so we have the 0, A. Okay, and now we just need to see the distance between each, so we just go over every one. We need to create a var L antinodes, which is an array. I guess we just need to add all the antinodes to every single kind. So this is not too difficult, I guess. So we need to for L print L antenna frequency, print L antenna pos. Okay, let's see if this works. Oh, okay. Antennas.key. So antenna frequency. This will be a string. And then in here we just get all the things from L frequency. And this will print some data. Okay. Okay, now we need to check all the distance between each one. And see if we can put an antinode on the other sides. I think we should get this into a different function. So func get anti positions. Give that that data plus L antenna position itself. L antenna, because we cannot put a antinode on the place of the antenna that we're scanning right now. So L antenna, if L antenna is the same as a pos, we continue. We should probably also check. I don't think if it's the same frequency we can add a node there. So we should also probably check if it's the same frequency. So exist in a frac. If yes, don't add. So I think I think this is what we should follow. Probably. Okay, give me a second to figure that out. Okay, so a couple of things have changed. Quickly checking in to show what I have right now. So I have a print map function, which just makes it easier to see if I'm printing the correct thing. It just prints the map with the correct version next to it. And I have a clean antinodes. In the clean antinodes, I will just delete entries that are outside of the map borders, because right now in the get antipos function, I basically try to go over every single one of them, and I append the L antinode pos. This is not working yet. I need to get the opposite, I think. I don't know what exactly is happening. I don't have any on the top right now, which is not really correct. Yeah, I just need to figure out what the correct way of doing this is to get the correct results. So what I first started thinking was to do this and just have a minus here over here as well. Minus, and that would, I think, give me the opposite. So, yeah, no. Okay, I need a little bit more time. Okay, so I think I almost got it working. I get the difference, but the difference is not correct anymore now. I was getting the difference. Like, I'm getting the correct difference, but again, math-related stuff. I've been practicing math since yesterday. I have been starting to practice math, and I'm using the application Khan Academy. And I'm going through the algebra, like pre-algebra course right now, because, well, my math is kind of bad. I think there's just a math issue again, like something that I'm not understanding correctly. The first position is the position of the antenna itself. So, okay, and I got it working. I made a mistake. I was deleting the nodes from the antinodes, but the problem is we get the order already from the for loop, and if we delete one in between, they all move up, but the number does not move up when we do the whole find thing. So yeah, I created a duplicate of the antinodes, reverse it, and then I use that information to find the data, and now we have a working solution. So let's quickly delete this whole correct data. We don't need it anymore. Over here as well. And I think now if we use data, the correct data, and we run this, normally this should work and we should get the correct amount. So normally I can select this, but it does not always want to work in Godot. Submit. Let's hope. Oh, I really thought this would be correct. Check distance of nodes and check opposites and save antinode. Check if same frequency exists. I think in an array you can append multiple the same ones. So we should make certain that we don't save ones that we are already saved. A anti-nodes. Let's do quick test. I think this is probably, yeah, okay. So we are probably saving the same anti-node positions multiple times. But, so we save these anti-node pose. No, I think this is correct. So 3, 4, 7. Please wait 1 minute before trying again. I don't know when I submitted it. Let's submit this. Let's hope. That's not the right answer. It's still too high. I don't know what exactly I did. I just deleted the other things here and now suddenly I have the correct result. It also prints 40. I don't know what number was for before. I should probably have checked that before submitting 2 false reports. But let's see if this is lower or higher. If this is same around like 380, then we're probably wrong. Out of bounds got index 12. Why is it probably you know what? Let's save this. Let's not remove everything yet because we may need it for part 2. I tend to delete my comments, like my print statements like that for checking, and I always regret it because I always have to type them again. That's the right answer. You are 1 gold star close to finding the chief historian, so I should just have checked better. Okay, part 2. Watching over your shoulder as you work, one of the historians asked if you took the effects of resonant harmonics into your calculations. Whoops. After updating your model, it turns out that an anti-node occurs at any grid position exactly in line with at least 2 antennas of the same frequency, regardless of distance. This means that some of the new anti-nodes will occur at the position of each antenna, unless that antenna is the only one of its frequency. So these 3 T frequency antennas now create many anti-nodes. In fact, the 3 T frequency antennas are all exactly in line with 2 antennas. So they are all also anti-nodes. This brings the total number of anti-nodes in the above example to 9. The original example now has 34 anti-nodes, including the anti-nodes that appear on every antenna. Calculate the impact of the signals using this updated model. How many unique locations? Okay, I don't think this is too bad. So we take this one and we just do minus L difference. So we don't add to frequency, but don't add out of map ons. I think this should be used for checking if let's not do this here. Let's do this over here. And let's just create a while loop. So, and we also copy this, but on the end. If this happens, we break. If this happens, we break. And we just keep doing, okay. And let's quickly print the test data again, because now this could be useful. So I'm glad I did not delete this. Let's do this, and let's comment this one out for now. A resonance. So if a resonance continue, let's just do, if it's not resonant, then we just go back. We have the new test data. Let's see what is different. So we don't have, we're kind of missing a couple. So on the bottom it seems to be fine. Over here things also seem to be fine, but we're missing one over here. I found my mistake. So my mistake was, this was 1 for some reason instead of 0. So now I get the correct amount, 29, but I also need to count all the frequencies themselves. I think the only thing I should do is just, if resonant, I dot append, and I just append a pos itself. So now we got way too many. So before we had 20. So let's quickly check. Is bigger than 1. Then we print something. Okay, so we'll print duplicate every single time when 1 is over it. So there are a lot of duplicates. So we should remove those duplicates as well. Yeah, I think this will work. So if you run this, this will be 34. And if you now take the full data, this should give us the final results. It doesn't, because we're using this still. I think I don't need this anymore, so I'll just delete it. If it does not work, I can always give it back, like put it back. But I think this, oh, and for some reason get live opens. So we have 1000. 233 and the other one is 327. So the first one is not broken yet. Let's hope. Yosh. Okay, so we finished day 8 and yeah, that's it, I guess. So as always, a big thank you to my Ko-fi supporters. If you want to become a Ko-fi supporter and support me, Gozen, and all the open source stuff that I will make in the future as well, please support me through Ko-fi. And whilst you support me on Ko-fi, you also have access to my resources that I offer for free for my members on Ko-fi in the Ko-fi shop. So thanks for watching, and I'll see you all in day 9. So tomorrow. Bye bye.